Hello, future scientists and engineers of Nepal. Ever wondered why a spinning top keeps going or how a skater spins faster by pulling in their arms? That's rotational dynamics, the science behind everything that spins, from bicycle wheels to our planet Earth. Rotational dynamics isn't just theory, it's everywhere. Opening a door, riding a Ferris wheel, or stirring your chia, all involve rotation. This branch of physics helps us design engines, washing machines, and satellites. So get ready to unlock the secrets of things that go round and round. Let's dive into the world of rotational dynamics. To understand spinning objects, we use three key terms: angular displacement, theta, theta, angular velocity, omega, omega, and angular acceleration, alpha, alpha. Angular displacement measures how much something has turned in radians. One full turn is 2p radians. Angular velocity tells us how fast it's spinning, radians per second. For example, if a fan blade turns 10 radians in 2 seconds, its angular velocity is 5 radians per second. Angular acceleration is how quickly the spin speed changes. When you turn on a fan, it speeds up. This is angular acceleration. When you turn it off, it slows down. Negative angular acceleration. Imagine a merry-go-round at rest. Omega equals sine 0. As it speeds up, it has angular acceleration. At steady speed, acceleration is 0. When it slows, acceleration is negative. You've experienced these concepts every day. Now you know the science behind them. If you know linear motion, you're halfway to mastering rotational motion. Every linear concept has a rotational twin. Displacement, s, becomes angular displacement, theta. Velocity, v, becomes angular velocity, omega. And acceleration, a, becomes angular acceleration, alpha. The radius, r, connects the two v equals sine rho and a equals sine array. The equations of motion translate directly. V equals sine u plus at becomes omega equals sine oo plus at, and so on. Every point on a spinning object has the same angular velocity, but points farther from the center move faster in a straight line. These simple relationships bridge the world of straight lines and spinning circles. In linear motion, mass m resists changes in motion. In rotation, moment of inertia, I, resists changes in spinning. Moment of inertia depends on both mass and how far that mass is from the axis. The farther the mass, the harder it is to spin. For a point mass, I equals sine mr2. Distribution matters. Torque, tau, is the rotational equivalent of force. It's what makes things spin, like pushing a door or using a wrench. Torque depends on force, distance from the pivot, and angle tau equals sine rf synth. More force or a longer lever arm means more torque, making rotation easier. Angular momentum, L, is the rotational version of momentum L equals sine IO. It measures how hard it is to stop something spinning. The law of conservation of angular momentum says that if no external torque acts, L stays constant. If a skater pulls in her arms, her I decreases, so omega increases, she spins faster. Divers, athletes, and even planets use this principle. As I changes, omega adjusts to keep L the same. This law explains everything from spinning skaters to orbiting planets. Conservation of angular momentum is a cornerstone of rotational dynamics. Rotational dynamics powers washing machines, satellites, and sports. Washing machines spin fast to push water out. Engineers use torque and balance to design them. Satellites use spinning wheels to turn in space, conserving angular momentum for precise control. Athletes use spin to throw farther or bowl trickier balls. Angular momentum in action. For your NEB exams, focus on theta, omega, alpha, torque, tau equals sine rf synth, and moment of inertia, I. Remember, torque causes angular acceleration, just as force causes linear acceleration, tau equals sine iia. Don't forget conservation of angular momentum, L equals sine io. Master these ideas and formulas, and you'll ace both your exams and real-world challenges.